still work if I just input all the values, right, instead of importing?
Yeah,
It would,
it would, yeah.
because when I, downloaded the information for this one, it only was importing the difference values. So I figured, I was like, I can just write those down, so only 11 values, you know?
Yeah,
Cool, cool, thanks.
you bet. Well, it looks like it's time. Welcome back, folks. Well, we've got a representative in Zoom. Thanks for making it, Casey. And we've got a person in class, so looks like that'll be enough for us to get started. Any questions at all, folks, before we jump in? Okay, well, we're on chapter number 18, just about to finish this one off. We'll take our time with it, make sure we get all of our analysis just right. Then we're changing gears. We're going to be looking into categorical data, which we haven't really dealt with for quite a few chapters now when you think about it. So this will be exciting, kind of a refresher on just new different landscapes for our statistical methods, different kinds of data types, starting in chapter 19. The other announcement, of course, is that our second exam is going to be next class. So we won't hold a Zoom class on Monday. For the in-person section, we'll just be holding that exam. And for the online section, the exam is open to be scheduled between the days of Monday through Thursday. So if you haven't done so, please be sure to schedule your exam. And that's pretty much my announcement so far. Assignment number 7 is due today, and that's going to be the last content that's on our second exam. So good strategy for studying on exam 2 is get caught up on the homework. Even if you're a little behind on any of those chapters today, I'll be accepting it and grading them as soon as they come in, as soon as possible. Be sure to take a look into, again, the formula sheet, the real last page of the exam 2, and 2 different versions of the sample exam. When I wrote the exam 2, I was very careful to make sure that these versions lined up pretty closely to the questions that I was going to write. This one is just brand new questions, so this is probably one you'd want to take a look at first for new scenarios, new analyses, I guess is a better way to pluralize that. But pretty much, it's just going to be the same kind of exam like we went through on exam 1. Same exact policies, and altogether, another piece of advice is it's going to be 4 problems altogether. One problem is either a hypothesis test or a confidence interval in chapter 14. Another problem will be finding the right sample size to target a margin of error, like you did in the homework in chapter 15. And a second chapter 15 problem is going to be looking into writing down what a practical interpretation will be for a type 1 error, a type 2 error, and for power. So it'll be concept heavy in that chapter. Then chapter 17, if we picked a, say, confidence interval in chapter 14, I'll ask one hypothesis test in chapter 17. And likewise, if I picked a hypothesis test in chapter 14, and I used a random number generator to pick the problem type, if a hypothesis test was chosen here, we'll go for a confidence interval in chapter 17. So that's going to be rounding out exam 2, and then exam 3 is just going to pick up where we left off, chapter 18 stuff. Well, any last questions or comments at the moment? Okay, maybe before we get officially started, Miranda in class pointed out there's a flaw in the homework assignment number 7 on one of the questions. So let's take a look into that right away, just in case that's caused some confusion. And that problem, let's say, let's take this right here. Hang on, I think a better way to download that is going to be go right here, assignment number 7. Let me download the Word version. And I want to download the data set right here as well. Now, I guess we're back in the thumb drive. Nope, over here. Here's the assignment number 7. We might as well fix this while we're looking at it and thinking about the assignment. The flaw is in this problem right here. The original data set looked like this, but I thought I'd save a step by doing the difference of the control minus, or excuse me, oligofructose minus control was my thought on that. But then the student pointed out in class that subtraction did not go as intended. This entire column is just negative of the control group. So we should fix that right here now. This is all incorrect information. I've got the raw data here. Oh, but that's just the difference. So we can fix that pretty quickly still. Let's go for RStudio. I'm going to call this control. We'll get 78.4, 76.6, 57.4, 51.5, 49. There's 11 observations, but we get this done right here now will be less annoying when we're doing the problem. 44.2, 42.9, 37.2, almost there, 34.1, and 24.6. Okay, so one in, then do it all over again. This is not the most interesting type of statistics, but data entry is part of the world of statistics, so let's make sure we get this one in accurately as well. I'll just abbreviate it to oligo. And now it's 62, 95.1, 46.5, 49.4, 89.7, 43.8, 50.3, 51.6, 66.6, 52.7, and 54. Let me know if you spot a number that looks a little bit off on those. Okay, so with those put in, I wanted the difference to go this way. Oligo minus control. Let's make sure that's the same order. That looks about right. And the number should have been one error. Thank you for spotting that. That was going to be invisible for me. There we go. Now we have the differences. So down below, here are all of our differences. Let's fix this file as well. A new version of Notepad is available. Let's just ignore that for the moment. The differences should have been negative 16.4, 18.5, negative 10.9, negative 2.1, 40.7, negative 2.8, 6.1, 8.7, 29.4, 18.6, and another 29.4. Okay, so our no file is fixed. For assignment 7, let's plug that in. That didn't go the way I thought it would, but let's try again. There we go, that looks a little bit better. And here's our whole revision. I'll just highlight it in yellow. Instead, red makes it look a little bit ominous, I would say. And again, sorry for that error. If you've been working on this problem and the data was looking strange, that could have been the potential reason to use that column. So we'll revise this. Let's throw it back into the assignment. Let me make sure I save that as well. Okay, so this should be now uploadable back into RStudio. Let me just double check. Okay, those look like the right values. And finally, back here, let's fix this as well. Here's assignment 7. Both versions and the corrected data set as well down below. Possibly, let me make sure that went to the right spot. There we go. Okay, so we've got this revised. And if you've already submitted the assignment and used different data, I'll be mindful of that and make sure you're not going to have points lost because of a weird error I made there, but let me remove that as well. Okay, again, probably not the best use of class time, but it's good to get those kinds of errors fixed as soon as possible, just to save headaches down the line. But assignment 7 is now ready to go. And again, the major idea is we're just analyzing the differences in that particular problem. The major reason in that particular example, in exercise 7, the data was dependent. The same individual used in the experiment had measurements done twice, their calcium absorption when they were not taking anything at all, and their calcium absorption when they were taking the so-called oligofructose. And when we compared against this problem that we were working on, the reason we're using an entirely different method for these data is this time we do have, in fact, 2 independent simple random samples. So this is what put us in the 2-sample T procedure. But once again, if the data is dependent and it makes sense to subtract the data, like on that exercise 7 in the homework, all we do is the 1-sample T procedure and we work it on the differences that we see here. Well, thanks for your patience on getting that correction put in as fast as possible. And again, this is the problem that we left off on class last Monday. Any questions at the moment before we get started on finalizing this example? Okay, well, let's refresh what it was all about. A thematic apperception test was done where mothers of 2 different groups of children were presented with ambiguous pictures. They had to tell a story about it. And then the experimenters scored on the TAT test the number of stories out of 10 exhibiting a positive parent-child relationship. So all these are scores on the mothers of normal children versus schizophrenic children. We wrote down mu1, mu2 is going to be the population mean of those scores for the 2 groups, for the mothers of normal children and schizophrenic children respectively. And then we formed the null hypothesis that there is no difference whatsoever between the groups. And for the 2-tailed test, alternative hypothesis, we're checking for a direct difference in any direction. Maybe the normal children have a higher score, or maybe the schizophrenic children. So this will allow for 2 different directions in the potential rejection of the null hypothesis. The next thing we worked really hard on towards the last part of class on Wednesday was just visualizing the data to see if it even met the criteria for using the 2-sample T procedures. If these data looked worse, if the outliers and the degree of skewness was worse, or if the shapes were different, both of these are right skewed, which is a big help actually, then the combined sample size of N1 plus N2 equal 40 may not have been large enough. But we didn't detect any major outliers. The data distributions had similar shapes. So using our robustness conditions up on the notes, we said this data does pass. So now we're on the step of computing everything we need for the test statistic and the p-value. So that's our refresher just on looking at the data so far. Any questions at the moment, folks, about the data before we go to analyze it? Okay, there could be, again, a lot of work that you do on this kind of problem. We think back on what we did with the confidence interval problem up here. It was not too bad to get the standard error. We used that particular formula. The degrees of freedom was touchier. We had to navigate a pretty big order of operations type problem, importing that into the calculator just right to get the value. Then the critical number T star wasn't too bad, but it does take some time to put the confidence interval together and then finally analyze it. The reason we had to work so hard on these data was there was only summary data provided. We didn't have all the raw observations. But in our current problem, we do have that. If we have the raw data values and we just want to run a 2-sample t-test, here's what it's going to look like. Go back to RStudio. This is our first part, just importing the data, separating the variables out of the data frame. And I'm noticing before I get started, I should import that data. So let's make that our number 1 step. import the data set. So this syntax is actually going to run. Okay, so with that available, let me run all this syntax just to get everything in line. So here's our observations. We're not too worried about the graphics, so we can leave them small. And now down below, this is going to be the entire test. Hit t.test, same exact syntax you would use in chapter 17. There's two independent samples, so we start by just putting them in. Norm first, schizophrenic second, and you can change the order, but if you change the order, keep in mind, you need to track which one is mu1, which one is mu2, especially if you're doing a confidence interval. So if you said mu1 goes with, say, normal children, you really should keep that order the same all the way through, because if things switch, it can get sometimes really very tricky and confusing to do the analysis, particularly on the confidence interval. So keep that order the same. Also, we're doing a two-tailed test, so let's write in alternative. There it goes. Here's the alternative hypothesis. It gives us several different options. Two-sided is ours. The two-tailed test is how we called it. You can also put in greater if you are doing a right-tailed test, or less if you're doing a left-tailed test. And notice the two-side interval is the default, so you actually don't have to put that in. But it's good practice to put in the alternative every time when you're practicing this, just in case it does switch to, say, a right-tailed test or a left-tailed test. We'll be ready for that. So here I'll just write 2.cited, and this should do the job for us. We have the data imported, the right alternative hypothesis. We have a 0 being the assumption for this test, so we don't have to put in any further information. We run the syntax. It does essentially everything for us now. It's kind of nice. We didn't have to worry about calculating, say, the degrees of freedom. It's just right there looking at us. Now, we had a combined sample size of 40 observations. And if we use the pooled two-sample t-test, this would have been a degrees of freedom 38. Combined samples, -2. The reason it's a little bit lower is we're not making any assumption whatsoever about the variances of these two groups being equal or unequal. We're allowing them to be different. And they're different enough to drop the degrees of freedom a good amount lower than 38. That's going to make our p-value a little bit larger, but at least it's a more accurate p-value in that one specific sense. But notice it's a pretty small p-value, so our analysis is done. We just have to write in the conclusions. So when you're doing these kind of problems in a complete analysis, be sure for this step to state what both your test statistic was and what your p-value was. You could also take a screenshot of just this output. That'd be a completely fine way to go. I'll go with the option of just writing it in. So test statistic is 3.0995. And the p-value for this two-tailed test, they've already doubled it, so we don't have to worry about going times 2. It's 0.003855. And that's kind of fantastic in a way. That took away a lot of just the nitty-gritty details algebraically of navigating through those formulas. So if we have raw data, just treat yourself to using RStudio. This problem was more about just giving the analysis, whether it met the conditions, setting up the parameters, hypotheses, and then finally giving the conclusion. The emphasis was not so much on the computational side, like on the confidence intervals. Well, any questions so far, folks, on running RStudio through this? Okay, so let's go back to the top. If we're going to give a conclusion, it's good to keep in mind exactly what your parameters are, exactly what the hypothesis test is, because we're making a direct conclusion on this where the alternative is. You either say you found significant evidence that that's true where the red dot is, or you failed to find that significant evidence. Avoid any statement that's going to convey you have evidence the null hypothesis is true, because the hypothesis testing can never gain up that kind of conclusion. So let's take a screenshot where we also stated the practical question just to make sure everything is in line with our overall conclusion down below. So we have a really small p-value. Our significance level alpha is at 0.01. So this is certainly less than 0.01 equals alpha, meaning we will reject H naught. And when we say we reject H naught, that means we have evidence for this. We just have to say it now in ordinary language that everyone will understand, using no specific specialized statistical language, special symbols whatsoever. So with that rejection there, we come back and say, we have evidence that that's true. Let's start by saying that portion. We have significant statistical evidence our benchmark for evidence was at that level right there. So I'll say at the 1% significance level, that, and I forgot to get a blue pen going. Let me get another one up here. Okay, so we have evidence that this statement is true. So let's read out what was mu1, what was mu2. We're going back over here and saying the mean TAT score for mothers of normal children and schizophrenic children are, well, it was a two-tailed test, so we can't say one is greater than the other. We'll just say are different to convey the not equal to 0 that we see here. So are different. And that's the whole entire conclusion of the test. We say we have evidence that there is a difference in these populations with respect to the average of the mother's TAT scores when we compare them against normal children and schizophrenic children. Really the same statements, just said in a different kind of way. So you're welcome to put in your own words. Make sure you mention the both populations. Make sure you say mean or average at some point, because this isn't about individual mothers. This is about an entire population average. And make sure you mention the quantity. If you say mean, you also have to say mean of what specifically. We had to say TAT score at some point. But one thing that we can step back now that we have that conclusion is, let's be honest, this conclusion is kind of awful, right? Because when people were doing a study like this, they're pretty interested in how these groups compare. The score looks like it's higher on average than the scores on the right, but we just said we have evidence that they're different, and we ended it right there. If you say presented this to a group of people, they're going to ask you a follow-up question probably almost immediately, and that follow-up question is, well, which group had the higher score then on average? You just said that they're different and you ended your analysis, but that's because the hypothesis test was really just the overall test. We look for a difference first, and the moment we find a difference, we have statistical significance, we move into a follow-up. I won't call it a test because it's not a test. We'll call this a follow-up procedure. So once we have statistical significance, we go even beyond in a typical real-world situation of data analysis. We found a difference of these averages. So now we're going to estimate these by providing and interpreting a confidence interval. So that's going to be our next level in the analysis. Well, any questions at all, folks? Getting through the complete analysis just for the overall test, the hypothesis test? Okay, and it's always good to keep in mind the reason we're doing a part B is hypothesis testing and confidence intervals absolutely do not exist in isolation. They go hand in hand. But if you're doing a problem, say as a homework problem, you only have to do the follow-up analysis that we're about to do if the problem specifically asks you to, or if you're just curious and you want to. So here, we're going to provide a confidence interval. But notice RStudio did that for us. There's a confidence interval right here, but there is a major problem with this confidence interval. It's a 95% confidence interval, and our significance level alpha was at 1%. We can't provide that confidence interval. It would be dishonest. If we found statistical significance at the 1% significance level, we have to make sure our analyses are completely compatible with each other. And that's what this comment in yellow is all about. The confidence level has to be chosen in a way that's based upon what we did in the hypothesis test by allowing for this. Select C so that C for the confidence level as a decimal plus the significance level alpha also as a decimal has to be exactly 1. So if alpha was at 1%, we would have C plus 0.01 equals 1. And that means our confidence level has to be at 99%, not 95. 95% just happens to be the default in RStudio. So to make sure we have the same kind of analysis, this is going to be our next step in RStudio. We want to control the confidence level in the t.test function. And so we'll write in this, go conf for confidence dot level. And once that pulls up, we would read the thing in yellow, make sure we're on the right track. Hit that and change it to 0.99. And observe that how the confidence interval is absolutely going to change. We should see it update to 95%, but you still put in a decimal here. So run the whole syntax. Now we've got a 99% confidence interval, and it's much wider than the one that we did above. So once again, when you're using RStudio, you can just pencil in or pen in the results. You can take a screenshot if you like. For this one, just to convey either way is just fine. I'll take a screenshot on this one. So here's our result using RStudio. 99% confidence interval. I only selected the part that was relevant to the question. The interval itself is right here. But we also have to provide an interpretation of the confidence interval. So we need to go a little bit beyond what we wrote here. Let's write in the moment that interval is down on paper, we have that 0.18. Let's think about what that number represents. Remember, the overall context was the thematic apperception test, and it was scored in a number of points between 0 to 10. So this is 0.18 points. It's less than a difference in population means, mu1 minus mu2, which is then going to be less than about 2 points. Let's keep this at, say, 2 decimal points, 2.82 points. So that's our confidence interval. Now, it's, again, we mentioned this before on our confidence interval problem that we did the first time in these notes. If you have 2 different values here, sometimes it is tricky to interpret these. So what I'll do is I'm going to solve it for mu1 and rewrite it as mu2 plus 0.18 points is less than mu1, which is less than mu2 plus 2.82 points. Okay, so now we've got our confidence interval in an algebraically equivalent form, one parameter in the middle. So we're comparing mu1 now against mu2. And generically, right at this step, you could say the population mean mu1 is from 0.18 points greater than to as large as 2.82 points greater than the population mean mu2. The only trouble with that is we need a practical interpretation, so we have to say exactly what mu1 is, exactly what mu2 is. But any questions at all, folks? Just getting to that point of the process. Okay, let's look up those parameters one more time then. Here's mu1 and mu2. We don't need the hypothesis test this time. We found that there is a significant difference. We found evidence for the alternative. But now what we're addressing is how big is that difference potentially? So that's essentially what our interpretation is going to be. We can write out just a generic process, mention the confidence level first. With 99% confidence, then we say what mu1 is. It's the mean TAT score for mothers of normal children. The mean TAT score for mothers of normal children Then once we have that down, we go to the difference we see. It's positive on both ends, so we can write out that, let me highlight it in this way just to show how it comes together, is from 0.18 points higher to positive again here, so I'll say 2.82 points higher than the thing that's higher than is mu2, which we just read out, the mean TAT score for mothers of schizophrenic children. And then at that stage, our analysis of the confidence interval is complete at that point. So it addresses on very well why we rejected the null hypothesis. Because the differences are always positive, mu1 is always larger in our entire confidence interval, goes hand in hand on why the p-value was less than alpha. If this was bigger than a 0.01, our confidence interval would have had a positive side and a negative side down here. So these conclusions interact with each other as long as you keep alpha and the confidence level so that they both add up to 1. If you switch your confidence level and have a different significance level alpha, you can have one conclusion here that's totally different than the conclusion here down below. So the hypothesis test is nice because it gives you an answer to a question of, is there a difference? But notice the confidence interval is even nicer in my opinion because it answers the same question and it provides more. It gives you an estimate at the same exact time. Now we can look at this with a more critical eye. The difference is pretty small here, almost 0 points, and it's just below 3 points. So even though we found significant statistical evidence of a difference, we have to ask ourselves, is 3 points on a thematic apperception test, where these are stories scored in a pretty interesting way, really that big of a deal, a big way to tell between the so-called normal children and the so-called schizophrenic children, as that was defined clear back in 1970. To me, that doesn't look like too big of a deal, but a lot of people might have different opinions on that. But at least with the estimate, the actual interval themselves, people can inform themselves of how they feel about the results, seeing this down here. We just left it here. We know that there's a difference. that leaves a lot to be desired in the hypothesis test. Well, we did it, folks. That's the entire conclusion of chapter 18. We're going to do even more with quantitative data. We want to look into quantitative data when there is even more independent populations, say 3, 4, 5, and so on. When we begin to do that, that's going to be the start of the analysis of variance type topics, or the so-called ANOVA methods for analysis of variance. But going in the order and the flow of what our book is presenting the chapters as, we've been spending about 5 chapters, depending on how you count them, on nothing but quantitative data. So now we want to turn it over for a quick journey and to see how to analyze some categorical data before we get into ANOVA. Well, any questions at all, folks, before we turn the page over to categorical data? Okay, so let's take a look. Before we get there, I want to point to one document that we're going to be building over time in this class. Now that we have 3 big chapters under our belt, well, we're starting the third one, chapter 19. One thing that gets a little bit tricky with this class is, how do you know when to pick each statistical method? And so that's what this document is all about right here. It's a document that's going to get bigger, grow as we go from chapter to chapter. But here's what it looks like so far. If we have exactly one quantitative variable we're analyzing, say we're doing the chapter 7 homework on control minus the oligofructose calcium absorption, we're just analyzing one variable, the difference. We would use the one sample t procedures for a mean in chapter 17. But we were just in chapter 18, and what separates it apart is it's more than just a quantitative variable here. And the problem we were just looking into, the quantitative variable was the TAT score. But that's just one variable. If you combine a quantitative variable with a categorical variable with exactly 2 outcomes, in our last problem, the categorical variable was mother of normal children or mother of schizophrenic children. It had exactly 2 outcomes. And that's what put us in the chapter 18 methods. The conditions have to pass. That's really 2 independent samples. The data is well behaved. But that's what gave us the 2 sample t procedures. Is the fact that there's one quantitative with one categorical variable mixed together. And the fact the categorical variable has exactly 2 outcomes. Make that 3 outcomes, and it's no longer chapter 18. We do ANOVA procedures on it. So now starting over, if there is exactly one categorical variable, nothing quantitative in sight, and even more, if there's exactly 2 outcomes, we'll be in chapter 19. If there's 3 outcomes, it's a different chapter. If there's 2 categorical variables, it's a whole different chapter again, and on it goes. So this is the role that chapter 1 was really trying to play. Understanding the type of data you're even looking at in the first place will inform you which statistical method you really are going to use. And then this is just a guidance on where to look in the book, where to look in Canvas to research those methods. So let's open up that chapter 19. We've talked about categorical data a little bit in chapters 1. It came up a little bit when we were looking into sampling distributions in chapter 13. And one thing we didn't really finalize when we were looking into chapter 13 is the central limit theorem for a population proportion. So now the notes have that information included. And the goal is to talk about that central limit theorem down below on the very bottom. But we're going to work our way towards it because just throwing that at you is like a lot of information, a lot of different symbols all at once. So we want to say, what is p hat? What is p? What is going on in this context? Starting at the very top by going through these definitions and an example below. I also put on the notes, just for the sake of comparing the central limit theorems, this is the one that we've been basing all of our methods so far in chapters 14, 17, and 18 upon, the central limit theorem for sample means. tells us the statistic, X bar, the sample mean, is approximately distributed this way, but we are only able to use the central limit theorem if we are dealing with quantitative data. So once again, the landscape is changing now. We're turning over to categorical data. So we have to change our central limit theorem to match up with the new data type. Well, here's how the definitions begin. It says, suppose we have a simple random sample of size n. So n is still going to denote the sample size. We're going to take n recordings for a categorical variable, but for this particular chapter, we're going to make the hard assumption there are only two categories for our categorical variable. It could be things like yes, no, up, down, something along those lines. So generically, if there's only two categories, we'll call one category a success and the other category a failure. Not that there's anything wrong with a failure. It's just if there's two categories, you can think in terms of yes, no, true, false, or success failures, how we're going to analyze. We think when we say successes, we're thinking in the terms of the success. Here, this is the object, or the outcome is a better way to say this. The outcome, the study, is focusing on. So once we determine what is the study really all about, it will tell you what the success should be in the problem. And word of warning as far as a success goes is, it's not always a nice thing. Sometimes a success is like the worst thing ever. If we're just discussing, say, a certain kind of cancer in a population, if that's the thing we're studying, then the member of the population having that cancer is the success, only because that's what the study seems to be all about. So it's not necessarily a good thing. It could be, but that's not what the focus is on. A success is just the focus on what the study seems to be all about. Well, once we have that, we have a new parameter. The population has true proportion P of successes. We'll denote that parameter by P. And instead of proportion, you could say percentage for the same information. But this is the parameter in the problem. I guess that's stated down below there, so maybe that's going to be too much writing. We leave that on there. The parameter is the unknown in the problem, and again, we said that down below. It's the unknown parameter P. And so to estimate it, suppose we took a random sample of size n. What we'll do is define a new variable x. It's discrete in the sense that x is just a count. It can't be a fractional decimal value. It's a whole number that goes from 0 to as large as n, so integer values. All it does is it counts the number of successes in the sample of size n. And once you have x, you define the statistic. The sample's proportion of successes will denote by p hat. There'll be number of successes in the sample, so x, divide by sample size n. And again, p hat could be conveyed as a percentage. This is just it written as a decimal number. We call it a proportion in that case. So p hat is the statistic. It estimates an unknown, the parameter p. So that means p is approximately equal to sample proportion of successes, p hat. But we have the same conflict that we had on the very first day when we were discussing statistics. Even though we have an estimate, that estimate right there is functionally useless to us until we can do the following. This is useless as an approximation until we describe the error. We call this typically margin of error. In the estimate. Kind of ran out of space there. Let me just go vertically that way. So that's our new landscape. We're looking at the percentage or proportion of successes in the sample. We'll estimate it, that statistic, will estimate the parameter, the proportion or percentage of successes in the population itself. And because this is a lot of new vocabulary out of nowhere, we'll run through it on a really fast, simple example, example one. But any questions at all, folks, with the new terminology at the moment? Okay, so here's a really fast context to think about all these brand new moving parts. The article, Facebook Etiquette at Work, in the year 2000 today, published in USA Today, reported that 56% of people participating in a survey of social media network users said it was not okay for someone to friend his or her boss. So that's pretty much the entire context. We're being told next, suppose this is based on a sample of 1,000 Facebook users. So they gave us a sample size there, n is 1,000. And there's no unit here. There's no TAT score type of thing that we're dealing with. There's no inches, miles, hours whatsoever. This is purely categorical data this time. They had 1,000 people, 56% of them said it's not okay for someone to friend their boss. Well, that sounds like what the study is trying to determine, what the study is focusing on. That's describing a success in this problem. So let's highlight this right here. Not okay to friend their boss. This describes the success in the study. For this problem to truly fit the context of chapter 19, data has to be categorical. It truly is. But even more than that, there has to be exactly two categories. But that's what we're looking at here. The respondents of this survey are either going to say, yes, it's okay to friend their boss, or not okay to friend their boss. Because the problem was, the statement of the context was indicated this way, we determined that this was the success. What the problem seemed to be studying the most is that particular outcome. That tells us what X is. Almost. Well, not exactly. We have a 56% here. Looks like X is unknown. We'll come up with that. I think that's part C in the question. But also told us that it was reported that 56% of the people participating in the survey fell into that outcome, the success. But this would then be the statistic. The word survey is referring to the sample 1,000 participants. It gave us a percentage of 56%. We typically write that statistic as p hat equals 0.56. That's actually part B, so let's put it down below there. So p hat was just given to us. I wrote it as a decimal, which is a really good idea for lots of the formulas we're going to use. It has to be in decimal form. So that's kind of a best practice when you write down the statistic p hat. But you can still think in terms of percentages. This is just saying 56% of the people in the sample, those Facebook users, fell into that particular outcome for the categorical variable. Next thing we want to do is describe the unknown parameter p. But we have kind of a dichotomy so far. Let's talk about that first. If our data is quantitative, there could be more than one parameter, but we're often talking about a population mean mu. There could be multiple population means. Chapter 18 had 2 of them, but we're not going to use mu this time when we see unknown parameter, because this time, if the data is categorical, we use p instead, which is going to be the true proportion of successes or population proportion of successes. So that's the symbol we're going to write down this time. P. I'll say, let's copy this language here. You could say population proportion of successes. I'll go with true proportion of, we don't want to say the word successes because we want to describe the parameter. I forgot to put in these words here. Usually this would be written by saying, using the context. Let me put that in red just to convey that was a quick edit on the instructions there. But that's the typical thing we've done for every parameter. We're not going to say true proportion of successes. We also have to say what the successes were in the very first place. So here's the successes up above. P will be the true proportion of, let's see, let's mention the population first. 56% of people in a survey of social network users made that statement. So it looks like the population would then be all social network users. Maybe it's just Facebook users, but this looks like it was a little bit more broad when it wrote it this way. So let's say true proportion of all social network users that, so the population is written in. Now we just say what the success is. That say, it is not okay to friend their boss. So that's our entire parameter. These are kind of tricky, and what's also maybe a little bit more tricky is this isn't the first time putting it down for categorical data, that most of the time when we wrote down a parameter and said what it was using the context, it was for quantitative data. It flows a little bit differently if it's categorical. For categorical, you can't say mean any longer. There's no average here, so saying mean or average is inappropriate. You have to say proportion or percentage. So that has to be written into the problem. Also, same thing we did over here, you have to say what the population is when we describe a mu or a mu1 and mu2. And that's what we were trying to achieve on this line. Let's write here, just for guidance on homework and exams, we must indicate the population. Next, when we were dealing with a population mean, say it was the mean TAT score, we had to say mean in the problem, and we had to say mean of what quantity. But for categorical data, when we're using the parameter P, we say proportion, then we mention the population, but then the other elements we have to put in there is this part. We have to directly convey that what the successes were in the first place, because that's what P is. It's the proportion of successes. We have to say what the population is, and we have to say what the successes are in context. So this part must be indicated here. We must state the success in context. So that's the deconstruction of a population parameter like P. Very similar to what we did with the population mean. The changes are, we say percent or proportion, and because we don't have units like scores or inches or miles, we mention what the success is relative to that proportion. Those are always kind of tricky in my opinion. Any questions at all, folks? Getting that parameter down finally? Okay, and last thing, if we needed to know how many successes were in the sample, some problems just tell you. They might have said 93 people or 983 people said it was not okay to friend his or her boss. Other problems can state it in terms of a percentage. But the good news is, if we restate the formula, P hat is equal to X divided by N. And X is equal to the number of successes in the sample. That's right here where the question mark was. X equals number of successes. So we can take this formula right here and just solve for X by this part right here, how many successes are in the sample. We'll just use uppercase X like the notes indicate. It's equal to n times p hat. Then we make a substitution. N was the sample size of 1,000 social network users. We multiplied by p hat, which was 56%, but we were going to mathematically multiply by this number, 0.56, or 56 divided by 100 if you prefer. And this would give us altogether 560 successes. So if the problem states a sample proportion of successes, we can always deconstruct it like this and find the specific number of successes that are actually in the sample. Well, that was our warm-up problem. Again, the whole purpose of this was just to break down how this variable X is working, how the sample proportion P hat is defined, and maybe more critically, how to put down on paper what the unknown parameter is, writing out the context. That's going to be the bigger thing that we're going to carry over to whenever we're doing a confidence interval, whenever we're doing a hypothesis test. We'll have to come back to this kind of exercise and rewrite the new parameter. So we'll always know what we're estimating, we'll always know what we're testing, and it makes the conclusion writing that much easier. Just getting that step out of the way to start. Well, we're definitely in the notes, but the next big thing we have to do is we can't do any statistics, whether it's a margin of error, like we were mentioning here, or it's a hypothesis test, until we have a powerful tool. And that powerful tool is this, the central limit theorem for sample proportions. So here's our new statement. It says, gather a simple random sample of size n for a population that has population proportion of successes p. So that's where the parameter goes. In a central limit theorem, we're looking for the sampling distribution of the statistic. We want to know what the probability model is. And we also want to know what the parameters of that model are going to be. And this central limit theorem answers all of those questions at once. The sampling distribution of the statistic p hat will be distributed normally, approximately. That normal distribution will have center exactly at what we're trying to estimate in the first place, the unknown population proportion of successes p. And the spread or the variability, often we'll call this the standard deviation of the normal model, is this entire structure right here. This is inherited from probability theory, from the binomial distribution. So we're taking that information for granted and using that as the variance, or excuse me, the standard deviation rather. So that's two big pieces. And let's take one moment to imagine what would happen if you're doing a hypothesis test now. Suppose in a hypothesis test, you have a null hypothesis that P equals something. It's a proportion, so it can't be like 5 or negative 12. Maybe it's 0.25. Then you go to run your entire hypothesis test. But when you run a hypothesis test, the very first step you take is you assume that that's true immediately. And if you've made that assumption, you know the value right here, and this is new for us. You'll also know that value. You know both the center and the spread of this normal model all at once when you assume the null hypothesis is true. So hypothesis testing goes way different than it did in chapter 17 because there's only one parameter, P. In our old central limit theorem, let's peek at it again for reference, there was two parameters, so we had to work really hard. There was the mu and the sigma value, and this is why we had to jump into a t distribution. We had to make an estimate on top of an estimate, estimating sigma itself there, changing the distribution. But not so this time. Here, it's a one-parameter family of distributions. That null hypothesis is extremely powerful. This gives both the center and the spread through the standard deviation here in green. Lost the red dot, there it is. It deserves an exclamation mark because that means we're going to stay in the normal distribution for this chapter. There is no t distribution whatsoever. So that's the central limit theorem. Using the central limit theorem, we can define a standard error. Once you have a standard error, you have the entire confidence interval. We'll use z stars. Here's what the confidence interval looks like. You take the estimate, p hat, add or subtract a critical number z star, multiply it by a standard error. It has that structure right there, which we'll define. And then your whole work is done. Now we can do confidence intervals. But I felt like before we just jump into that, we just stated a really, really deep theorem about probability theory. We should do at least one exercise, that's going to be example 2, on just using this central limit theorem directly. And this will be the first homework problem on the chapter 19 notes as well. Okay, so we've got a central limit theorem that we're going to use. The problem has a lot of context because if you're going to write down a problem that seems like a legitimate use of a central limit theorem, there's just a lot of information going on in the background. So even though this problem is fictitious, it's a pretty realistic and believable one. It starts off by saying, Chantix is a medication prescribed for smoking cessation, quitting smoking is how I'll say it, that works by targeting nicotine receptors in the brain. So this is a real medication. The context below is fictitious, but very believable to what they would have done developing this drug. And to make this seem more relatable, let's assume that you work for the manufacturer, Pfizer. Assume you're part of a research team tasked with evaluating the efficacy, how effective it is, of Chantix. The very first thing you're probably going to do is a power analysis, just like we looked into in chapter 15. So it says, after a thorough power analysis, it's been determined that required sample size for your study is going to be 1,927 smokers. It's kind of a weird, odd number, but they're trying to do the study effectively and as cheaply as possible all at once. So they landed on this number, 1,927 for the sample size. And these are people who are interested in quitting smoking, so Chantix is relevant to this group, this sample. Now, after doing that power analysis, there's more things we want to resolve. Before even selecting the sample of those smokers, the drug maker Pfizer requires that further analysis be done on the potential outcomes of this study. Because if things don't go right, they could get bad publicity and then lose all profitability on this drug. Pfizer believes this drug will be profitable as long as the true proportion of Chantix users who successfully quit smoking within 12 weeks is at least 70%. So this is something done in the back office. All of the financial people, all the stock market people got together and said, it better be at least that effective. So they defined a parameter. Here it is. P is going to be the true proportion of Chantix users that will successfully quit smoking within 12 weeks. And even though we haven't even selected the sample of 1,927 smokers, we're going to make an assumption to see just what could happen in the study. So this is a type of real-world what-if analysis. Pfizer contacts your research team and asks you to determine the probability that the sample proportion of successes is 0.68 or lower. They're assuming it's 0.7, and that's probably a hope of hopes. Under the assumption the true proportion is right there at 0.7, they want to know the odds that you select a sample of this many smokers and the proportion of successes in the sample comes out even lower than 0.70. Pfizer's determined that Chantix will get that publicity and will jeopardize the success of this drug on the market if that happens. So they want to know what is the chance it's going to happen. If that's a really high chance, They might not even do the study whatsoever. They might just end the whole project right there. The chance is small. They're going to gamble, go forward with this study, and see what happens for the outcomes. Again, they made a major assumption right here. They assumed the parameter is 0.70, that 70% will successfully quit smoking. Now they're wondering, what's the chance this occurs? Here they're talking about the statistic p hat up above. We have a parameter p, we have a standard deviation because we assumed a value down here, much like you would do if you were doing a null hypothesis and an alternative hypothesis. So to answer the whole question, we'll compute the probability. In chapter 13, we had X bar inside of here, but the data is categorical, so now p hat is inside the probability set function. We want to know the probability that p hat is less than 0.68. They said 0.68 or lower, which conveys a less than or equals, but for a random variable distributed normally, you get the same probability, whether you wrote it as strictly less than or less than or equals. I'll go with less than or equals just because that's how the problem seems to be conveyed. So that's the probability we have to compute. But in order to do this computation, you have to know the probability distribution of p hat, or because it's a statistic, we call it the sampling distribution of p hat. It's distributed normally, so in RStudio, all we need to calculate is p norm. P because we're doing a probability, norm because the normal model is relevant here in this problem. We have to have the number of expected successes and failures both exceed 10, but we're well above that benchmark with this many users. So we're going to get a very accurate computation. We come back here, inside the p-norm function, plug in 0.70. So that'll be the center or the mean. The spread or the standard deviation is that entire structure. So we put in square root. SQRT is how we would write that in RStudio. So I'll use the same type of syntax. SQRT for square root of 0.70 times 1 minus 0.70 divide by the sample size n, 1927. And that's our entire computation, or the entire syntax that will give us the computation. So that's the whole direct use of the central limit theorem. The moment we made an assumption on the parameter p, we had a model to work with. So going back to finalizing this what-if analysis, here's what the results are going to look like. We're going to take p norm, 0.70, square root, 0.70 times 1 minus 0.70, or you could say some time and just put in times 0.30, divide by sample size, 1927, close the parentheses for the square root, close the parentheses for the p-norm function, and this is our probability. Well, almost. I've got like 6 different errors, it seems to say. I think that's a graphic problem right here, potentially. Let me see if I can run that again. Same problem, hang on. Trying to output a graphic. Delete that. That should go away, so let me try it one more time. No, it's still really upset with me. Let me see if I can fix it by extending here. We're down to 3 errors. Let me take a look at my syntax closely. I have a p norm, comma with the square root, times. Interesting. You know, sometimes if RStudio is just not behaving well, one strategy is let's turn it off and run again and see what that does for us. Okay, this is now a fresh environment. Let me try that syntax one more time. And That's about what I was expecting. Except there's one mistake here. So I've got the two values right here, okay, but my mistake was I never plugged in the 0.68. So let me fix my syntax a little bit better. This should have been equal to P norm. And this was my major mistake. 0.68 should have gone into that very first position right here. Then you throw in the mean, where this was the mean we had right here. Then you throw in the standard deviation, where we used this part right here as a standard deviation. And my omission was when you go to write out p-norm, you have to know the number you're putting in the very first place. This is relative to the sample successes being 0.68 or low in proportion. So let's try this one more time. Sorry for the errors on this. 0.68 with a comma. And that's the number I was actually expecting. 0.0277 upon rounding. So this comes out as a 0.0277. So that's our direct use of the central limit theorem. So what this problem is telling us is if P equals 0.70 is accurate, then, well, this was about P hat. So we can say then there is a 2.77% chance of selecting a sample where this outcome occurs. The number of successes is 0.68 or lower. Or we could say it this way, 2.77% chance of selecting a sample where 68% or less of the smokers successfully quit smoking using Chantix. So that probability is kind of small, but again, this is going to depend on the back office, the financial people at Pfizer. If it's worth risking about a 3% chance of getting less than 68 people actually quitting smoking, potentially getting bad publicity on the drug, which will then cut into their revenues when it hits the market even further, they, in some realities, might have just quit the entire operation and never developed Chantix further, never did any further testing. They eventually did. Chantix is available on the market. It's a pretty weird drug. So that's why we're kind of picking on it on this problem. But a major goal on this one was just to actually use the central limit theorem for proportions, see how it works in a pretty realistic type of scenario. You'll do another scenario similar to this one, different kind of context as a homework exercise. Well, next things we have to look into is what is the standard error, how to put together the entire confidence interval. But we'll do all that after we come back from the exam on Monday. We'll be back to this spot in the notes a week away from today. Any last questions at all, folks, before we call tonight? Okay, well, thanks for your hard work, everyone, on getting through this stuff. If you have any questions whatsoever when you're studying, working through getting caught up on these sections, don't hesitate to reach out. I'll be working on keeping everything graded as soon as possible across the weekend. And even if you send me your homework on, say, before maybe 5 o'clock on Sunday, I'll be able to make every opportunity and every effort to get it graded and have solutions sent back to you Monday morning on the next day. If you send me homework on Monday, I still might be able to get it graded and send it back to you on time, but it's going to be on a first come, first serve, case by case basis. But have a great weekend, folks. I'll see you all a week from today. Unless you're in the in-person section, I'll see you all in class next Monday. Take care.